Yeah, thank you, Prasadini. A warm welcome here from my side in summer Germany, early my time, but which is hopefully more convenient to your morning times. Um, yeah, having said this, we would start directly diving into a topic which drives me and us as a company quite much. Really, I think safety in a new evolving infrastructure, hydrogen and its derivatives like ammonia, like methanol, really traveling around the world, listening to customers and really helping in projects locally and globally as well. What you can expect from a company like us here, we roughly 16,000 employees around the world in almost 50 countries. We have direct sales and service offices. That means what you can expect from us is really working together with you locally on these projects, really looking into the details, looking into your challenges, what is upcoming here. We are family driven business, and this is also part of our culture, so that we really try to come in close contact with you. So where am I currently? Here's Europe. Here's our headquarter close to the Baltic Sea here in Northern Europe. Yeah, as you can see here on this graph, we have a lot of production side logistics centers and sales and service organization also here in Mumbai, taking care about Sri Lanka as well, from India, and we are very active in almost all continents. So what you can expect today, roughly in 45-50 minutes, I give you some overview about the markets, how we see, let's say, the new upcoming market, and I will give you some statistics as well. Then we dive into the production, the hydrogen production, mainly electrolyzers. What is it? Why is it so challenging? What do we see? And then some codes and standards. So that means what needs to be known to really maintain and set up a safe infrastructure. And at the end, one thing is what needs to be known. The last thing is what needs to be known to really make it safe. So that means also from the perspective of an hydrogen production facility, what needs to be known to be safe in terms of explosion protection. As I said, market perspective first, dive into that, how we see the market. So when we look here, let's say in the middle, this is what we are talking today. We see the main production for hydrogen is electrolyzers. There's also natural hydrogen underground deposits that raise up in some continents, but the major part will be electrolyzers. And around that, a total new ecosystem is currently evolving. We know this from the past, from centuries away, when oil and gas really influenced our whole industry. Hydrogen, ammonia, methanol will take over parts of it, not everything, parts of it, because we are still, since for decades, dependent on oil and gas. This is for sure. So what we see here is really the whole part of mobility, which is really difficult to decarbonize. One thing is for sure electromobility, when we talk about trucks, cars, and so on. But it will not solve the whole game. We see tremendous amount of projects in a fuel cell and the whole fuel cell business, which also has challenges in terms of safety for sure, but this is manageable. Then we talk about the big part of feedstock for industry, especially the steel industry, is really looking with big of investments, really looking deeply into decarbonization. So that means direct reduction furnaces currently deployed. So really going from pilot. We have several projects here in Europe. I know that in other areas in Asia as well, like in India, Tata, in Nippon Steel, in Japan, and in US, they're really looking very concretely into decarbonizing this CO2 intensive processes. And the same counts for chemical, cement, and fertilizer, which are major CO2 emitter. Yeah, the whole logistics around that, especially when we talk about ammonia, shipping around the world is currently a thing that pops up in really a lot of projects. And then last but not least, that this may come later, district heating, so that we either use natural gas pipelines. We have pilots here in Europe as well, and blend this with hydrogen, or let's say on long term, use hydrogen only. But this is, let's say, on a long term. So how much and how many projects do we see? Currently, I have with my team here quite good overview about roughly 1,200 projects, and this is really going up a lot. And you could say, okay, a lot of these projects are really long term, and yeah, we don't see them really concretely. But this is not true. So we have a database here in the background and a partner who helps us up. And you see here how concrete they are when we talk about request for quotation, which is a good indicator that in 24 and here beginning of 25, a lot of these projects really going active, and they are huge, what you can see here in terms of total investment volume. So it means really around the world. I quite recently I was in South America, in Chile as well. We see big investors like Fortescue from Australia who investing a lot around the world, and India. What we see here in this whole region in terms of who is really, let's say, investing and looking into projects, India and this whole region, including Sri Lanka, is really looking very closely into that. So that gives me and gives us here a clear indicator. Hey, this is not only a buzzword, this is really reality. This is a new reality. But some statistics, we have to, my goal and our goal as Dräger is really looking into, let's say, the safety, because this is one of the biggest threats, I would say, and challenges from turn it a little bit. When we looking to established industries like petrochemical industry, safety is, let's say, in the genetics. So this is part of company culture. When we talk here about, let's say, new industries, also new groups of people who are not so safety aware, that we here education starts. The sensitivity about new substances here, new technologies, definitely needs to be very present. And this is currently where and how we are working on it. There are organizations like the European Industrial Gas Association, which really looking into hydrogen-related production, storage, handling, and road accidents. They analyze that, and only 20, and not only, but 21 of these accidents, this is 10%, have been happened in the last decade. And there, for sure, purely from the statistics part of it, it will be more because currently the projects are going live and hydrogen. And this was related where we did not have the bus after the Green Deal and after the all the local hydrogen governmental strategies. So that means looking into that and looking even, let me take my mouse here a little bit away, looking a little.
Oliver, you went on mute.
Oh, now I'm back. I'm sorry. Thank you. Hydrogen tools, hydrogen safety panel, since decades is really looking into a very detailed analysis. This is what we can take out of these statistics and looking really into that, and taking this information to give you an even better service. Main reasons for hydrogen incidents. So we are working and we are member of the Center of Hydrogen Safety, which is a non-governmental organization, including lots of companies who are working since decade in this industry. When we just look into that, um, the causes of incidents were analyzed over dozens and hundreds of incidents. We see here a kind of pattern. So we see here valve malfunctions, leaks, leaking connections are the majority of it. So this is in percentage. It means over 35% are really caused by leaks. Looking a little bit deeper into that, when we said, okay, what are and where in the process it happened, we see here really in the operational part. So when it's going live, when we're doing regular maintenances and procedural operations. But here's also a kind of pattern where we have to look in. You could say, okay, here, especially in A, which is a fourth of all courses. No, A, B, C, and D, there's a pattern. This is people-related business. So either in planning and designing, in maintenance, in ramping up. So, and this is more related, let's say, to material, which is also important to know what kind of materials we have to use. Failure is also a part of maintenance, and hydrogen has some specific um, behaviors like embrittlement. You may know this. So that means also looking into that, choosing the right steel quality as well, is and the right fittings and discs and sealings and so on is very incremental to know that. Just to give you, let's say, an overview here about where we and which is our mission here is really to educate people so that let you know what you have to know to start your safe operations. Interestingly, I'm in contact with a lot of insurance companies because there's an insurance perspective as well. These are big insurance companies who, in your operations later, will be in. There could be local ones as well. I just choose here one, two, three from Europe, which are large insurer, and they see this as well. I've been invited to some of these risk management conferences in insurance companies, and they're telling the same story that currently if the risk and the process is not fully understood by the people, also from this perspective, the insurance rates will have to be raised. So that means if you could show that you did everything which is technically available, and this is also your liability at the end, and you could show a proper safety concept, which is state of the art, then let's say the operational cost in terms of the insurance rate will go down. And this is where these guys are really looking in. And the biggest insurer worldwide, FM Global, has published since years already a so-called property loss prevention data sheet. And there's a new revision from January this year, which gives you a good, let's say, good recommendation what needs to be known, what needs to be used. And there's also a special about flammability of hydrogen. So there's really a lot new good information. And as you can see, this is not from an industrial peer organization. This is from an insurance company. So that means they take it very serious as well. We want to talk today about hydrogen production. So that means electrolysis. A little bit going into the history because this is not new. Water electrolysis is known for over 200 years already, really by Antoine Walter. Nicholson, Carlyle, Ritter, and you may have had this experiments in physics lessons in school, where you have these two different cells, the cathode and the anode, and both hydrogen and oxygen. So that means water will be cracked, and hydrogen and oxygen will be produced. So this is a quite old principle, and vice versa. The same principle counts then for a fuel cell, where you bring together with a membrane hydrogen and oxygen, and you will get electrical energy out of it. So this is a quite old principle. And also, let's say the first electrolyzer stacks are quite old. So it's roughly 100 years. We see here from Norsk Hydro in Norway, which is, as you can see, a quite old system. They had used hydropower and still using today hydropower for larger renewable hydrogen production in Norway. So they have a lot of experience with that. And what you can see here, these kind of technologies still exist. So it doesn't has changed dramatically, with all, let's say, the safety consequences at the end. As you can see, these are pressed stacks. Here are membranes in between. And for sure, degradation is still today one of the biggest risks in let's say the electrolyzer technology, because when we talk here about proton exchange membrane, you may have pressures, internal pressures up to 30 bars. So differential pressures, temperatures between 40 and 90 degrees, which is not dramatically high, but for sure the biggest risk in PEM technology and with alkaline electrolysis as well, which is a little bit different from the technology part, is, let's say, crossing H2 into O2 and O2 into the H2 stream. And this, as we know from the school experiments, is very dangerous. So these kind of things are the biggest technology challenges that all electrolyzer OEMs are currently facing, and we are in contact with dozens of them, really looking deeper into that. But there are new technologies currently in preparation, I would say, for example, solid oxide electrolyzers, which is also, let's say, not new, developed in the 80s, but going really, let's say, compared to PEM and compared to alkaline, this has a quite low market share still, but it's going large and going larger. And for example, anion exchange membrane as well. So this will be scaled in the future, and there are a lot more technologies currently being developed. I'm in contact in some startup networks, so this is very promising, and for the future. That there will be a lot more, maybe safer technologies as well. But currently, the majority, I would say 95% of all large installations are either based on alkaline or either based on PEM. You could ask us, hey, when to use what? There's a rule of thumb. I'm not really a deep specialist here because my home turf is safety. PEM is mainly used when you expect maybe shifting let's say, energy input from wind, from solar, where alkaline is mainly based on having a very stable electrical input. And this is, let's say, the main difference here. So loss of containment, what are so-called safety vulnerabilities? So first of all, you have to identify the hazards as well. Hazards, as I mentioned, can be an H2O2 mixture in, let's say, the electrolyzer. So it means it is a cross-cell leak, and it can happen that you, what can happen is an internal combustion, loss of containment as well, for sure, because this is, we want to produce that and don't want to get into losses. Another ISV could be, let's say, overpressure. Can lead to failure of the vessels, of the components, loss of containment as well. We have a liquid electrolyte. can cause corrosion in sealings, in fittings, and in chemical burns. We can have an unintended H2 release into the air. So that means that this needs to be controlled as well. Either you have a controlled environment for the electrolyzer, that can be a container like seen here in the small picture, or maybe in a building. Some of the installation that I've seen are outside, but there are pros and cons in terms of durability, in terms of atmospheric weather, climate conditions on an electrolyzer. So both have pros and cons. Yeah, oxygen release for sure. There is an increased propensity of combustion when because you produce hydrogen, and in some installations I've seen the oxygen is just released. If there would be an unintended H2 release, a purging or an overpressure, it could cause also kind of atmosphere, which is then highly explosive as well. Because hydrogen has one big challenge, is a very, very, very low ignition energy. It's over 10 times lower compared to natural gas. Yeah, low temperature can happen as well. Water freezes and expands in some areas, maybe not in Sri Lanka, maybe not in India, but here in Europe, Northern Europe, over winter times when it's an outside installation, it can happen. Yeah, electricity, for sure. We talk about high power volumes here, high temperature as well. This is what we see also, let's say, outside temperatures as well, what we see in Middle East, for example. Yeah, some bypassing now away a little bit from the technology. What needs to be known in terms of codes and standards? What is already regulated? What needs to be regulated? And there's also a big difference between from where you get the systems or where you want to install the projects and with whom you're working together. So there's a big difference between NFPA, North American standards, and codes, and ISO and IEC standards for the rest of the world. And I will talk a little bit about consequences for that. But overall, we all have a duty to protect health and life. Why I'm saying that? This is based in your law, also in your national laws. And from a company perspective, this is something where you're at the end, the owner of the company, the CEO, is liable if someone gets hurt or even bad. So there are for sure basic laws which needs to be known, legislations concerning health and safety at work. So this is legally binding stuff that you definitely have to know. Accident prevention regulations, collective agreements, and so on and so on. And then are state of the arts. Standards, principle, as I said, norms like ISO, NFPA, technical rules about hazard substances, action plans, governmental action plans as well. So this is given out, and this needs to be known. This is not an excuse not to know about it. As I said, especially insurance companies and banks as well. So that means the financing part of it, they audit processes. They have own auditor, especially in these new applications, and they're looking into that. And as I said, this is not an excuse not to know about it, especially when we talk about safety in this whole context. The good thing is there's help. When we just look, to standards and codes across the whole value chain in the US, you could say, okay, why the hell I have to take care about US? You may in the projects get equipment, and this is normally internationally via, let's say, EPCs companies. So that means it could be that these OEMs are really used to use, for example, NFPA. And I will come a little bit later into that, what kind of standards are applicable here, NFPA standards and codes. So that means, when we just concentrate here on this left part of production, the CSA standards are applicable, UL, and for sure, when we talk about sensors and detectors at the end, NFPA will play a very important role here. Internationally in Europe, or let's say other continents as well, ISO, Senelec play a role. And as I said here, I've mentioned this already, the European industrial gas associations have given out also codes and standards and regulations, guidelines as well, which helps a lot to plan a proper safety process. Just, looking a little bit deeper into one specific international standard, the ISO 22734, which is dedicated to hydrogen generators using water electrolyzers. So this is something what you definitely have to put under your pillow and which you definitely have to look into. This is really a consensus built via multinational ISO processes, latest published in 19, and there are addendums currently working on, also working groups who really looking into additions, especially for the new applications and new technologies that will come up in the next years. We are partly working in these groups as well. This definitely needs to be known. The scope here is really from construction, safety, performance requirements, and what you can see here reflecting also the different technologies that I've just mentioned. So that means PEM, anion exchanged, and KOH means the third technology that I've mentioned here. Yeah, and for industrial, commercial, and residential users. Requirements, as I said, operating requirements, the gas quality is mentioned here, specification, very important, how you do a risk management and a risk analysis, what kind of equipment needs to be known, how it needs to be certified, how service personnel needs to be protected at the end. Test methods are described here and recommended, strongly recommended from this part here. And at the end, for sure, documentation. So what you have to have and have to show an auditor, for example, in terms of marking, labeling, and documentation. So this is really an central document, which gives you a quite good overview about what needs to be known, also in terms of, for sure, safety. Yeah, looking a little bit into the other side, NFPA 2 and NFPA 55. Here are references made between these two standards. What you can see here, hydrogen NFPA 2 is focusing really on hydrogen technology codes. It's really for production, as I said, storage, transfer, and the use of hydrogen in all premises. Includes also outdoor public refueling. That means this is also quite important standard which needs to be known. And there's a big difference between ISO and NFPA. ISO states you should do this, so there's a lot of should requirements versus an NFPA is really looking into a shall requirement. So that means you have to do it. It's not just you can't follow it, you have to do it. Yeah, looking into that, these technology codes really prescribes hydrogen generator requirements, so that the electrolyzer shall be listed or approved by a safety authority. The materials other than H2 shall be contained, and so on and so on. So indoor electrolyzers, very important, shall require ventilation as prescribed by a manufacturer in NFPA 2. So all these things are really in detail described here, what needs to be known and what kind of safety, and this is very important, safety infrastructure you have to have. And I will come later in my part of explosion protection a little bit, what does that really mean and what is really necessary to take care about. Especially NFPA 2 for detection systems, really looking into, let's say, shall requirements. Gas detection equipment shall be listed and approved and shall be designed, installed, tested, inspected, and calibrated according to manufacturer's requirements. Maintenance, inspection, calibration, testing shall be conducted by trained personnel. So there, as you can see, NFPA really states more a shall requirement versus an ISO is a little bit weaker. You could say, is it good, is it bad? I would say I would strongly go for do it. Otherwise, if it comes, let's say to an incident, and then you have to prove that you've done really everything according to standards. Yeah, having said this, hydrogen equipment enclosures is also part of that. So that means, the where hydrogen is stored in terms of quantities is in detail described. Where you produce hydrogen, when we talk about electrolysis, you have to store it as well, at least immediate. Maybe you transport it later, but this is part of this whole process as well. And yeah, let's say emergency and shutdown systems, fire detection is definitely a very important part of it. And the combination of gas and fire detection in one system is something which is not only recommended, which is also described in these standards quite intensively, and needs to be known here as well. And the type of detection shall be, this is not, let's say, just you could do, shall be determined by a risk assessment. So it means you definitely have to know your processes, or what people are involved, what is your environment, looking really in an hazard identification, and then setting up a proper risk assessment process, and then really looking into the details. At the end, I will come to, let's say, the part of explosion protection. So what does that really mean in terms of where can I expect the hazards and what kind of sensors can be used here? It mainly starts locally, let's say in your groups, with your safety engineers, with your board of management, with, let's say, a workshop. Maybe your health and safety officers, maintenance guys, operation management sits together, and you're asking yourself, okay, we have to identify, let's say, all new hazards in these new work activities, and we may need maybe new standard operating procedures for this. Big question is from management, do we know all the new regulations and standards? Because I'm liable at the end if it comes to an accident. And big question, how we define our new safety goals, because this is a new process. So what kind of safety needs to be reached? Yeah, this can be done in a risk management process. Either you do it on your side, either you do it, you can pull us in as a company as well. So we are doing these workshops with you together, and really looking, let's say, into the details from looking risk identification, the analysis, and then the evaluation, and at the end, risk treatment. So really what needs to be done at the end to bring, let's say, the risk down to an acceptable level. 5 important questions. 5 is good, 5 fingers. What are the individual substance properties? So that means if you use hydrogen or ammonia or methanol at the end, for sure, you need to know, okay, what is so different and what is so special? Second question, what amount of hydrogen do I expect? Not accept, expect. In terms of storage, in terms of pressure environments, low pressure, high pressure, maybe even liquid. So that means that needs to be discussed in this part as well. And then at the end, what kind of damage scenarios can occur, either locally or in the environment? Maybe you have a, let's say, public infrastructure around as well. Hydrogen, as I said, has a highly destructive explosion potential. And this definitely needs to taken into consideration here as well. What type of activities are performed, let's say, in my environment here? It's just an example in this picture, but then maybe there are other activities. Maybe you're planning to build in a hydrogen facility electrolyzer in an established environment already. it could be somewhere, as I said, when we looking to feedstock for industry, it could be a steel environment. There are maybe other activities already performed. Do they interact with, let's say, the new installations, with the new hazards that I maybe have with hydrogen in hot environments in the steel industry? So steel was just an example. We this year we started to work with the World Steel Association, working together. We have a partnership here and working currently very closely with a lot of steel companies around the world. Really here looking into the details and proposing and just giving knowledge out there exactly to answer these questions here. And last but not least, what kind of safety measures have already been taken? For sure, you start not from zero. The question is it enough? Or maybe we do an extra layer here of safety management. So how this is done, when we see a planned life cycle from concept over scope and risk, here you're looking into the requirements, planning, scheduling, then the construction. So this takes a long time, and where and how safety will play a role. What I can tell you as a thumb of rule, the earlier the better, also in terms of costs, in terms of identifying hazards, and let's say discussing the safety goals at the end and reflecting the current standards and codes that I've mentioned in my presentation. And then you develop a concept, you assess and review everything, and for sure the risk prevention planning, the training of staff and so on. Emergency and crisis management is part of it, especially for management. If it comes to a larger accident risk, which can happen, but you need to be prepared. Also, everyone exactly needs to know to work with whom, what needs to be done, not to get in panic, so that really everything is described in processes. Yeah, what kind of tools can be used? Definitely today I cannot look into the details, like risk matrices, like LOPA hazard studies. May you know a little bit about these tools already, but these are standard tools that are used, especially when we talk about safety concepts. Yeah, fire and gas mapping and modeling is a tool which we use very often. And I will tell you why and how this is done. For sure, training and reporting, no doubt about it. Explosion protection. There's a primary explosion protection. Primary means preventing already explosive atmospheres. So that means for sure preventing gases to leak, no doubt. If everything is gas tight, we don't have an issue here. We have to remove gases quickly. That means ventilation systems, for example, maintenance, purging, and so on. And you have to detect gases quickly. So that means the earlier you detect, the lower the probability that you get in explosive atmospheres. Hydrogen starts from 4 volume% in the atmosphere up to 75. So that means everything below 4%. Let's say the earlier the better, then you can trigger measures already. This is the reason why gas detection is a primary explosion protection measure. Secondary is preventing ignition sources. So, for example, you have an explosive atmosphere. If it gets not ignited, then it's let's say you don't get let's say an incident. So certified equipment for sure, mechanic instead of electrical equipment. Why is this mentioned here? Steel industry, for example, I've seen projects in the mobility part when we talk about refurbishing, or not refurbishing, but modernizing trains going from diesel to fuel cell. They have to be maintained somewhere. And in most cases, these kind of facilities, maintenance facilities, large halls, are old. So it means they have a lot of mechanical equipment, maybe on the roof, or electrical equipment, which is not X certified. So that means also here you have to look into the details. Maybe you have a leak somewhere, it goes up to the roof, and there you have an old electrical installation, which can maybe ignite then the hydrogen cloud on the roof. So that means you have to detect on the roof, have detectors on the roof, really to mitigate this risk as well. The tertiary, last but not least, constructive, so really prevent and reduce damages if it comes to an accident. Retardant materials, pressure relief valves, areas, roofs as well, evacuation marking ways. So at the end, gas detection is a primary explosion protection measure as really preventing explosive atmospheres in the first place. That's the reason why this is so important. Standards for detector selection. This is in document as well, which you have to put under your pillow. The ICA TR84, the guidance on the evaluation of fire, combustible gas, and toxic gases. It was to analyze chemical processes and hazards, from other industrial facilities. Design systems from performance-based perspective. You can see here that everything is really related to risk reduction factors as well. So it gives you a very good guideline what needs to be known and how to do it. It's really more the how, the layout, the define of quantities, and placement of flame and gas detectors. So it means, and it gives you, let's say, a percentage of coverage targets for mapping studies. And there's an addendum currently out in 24, which really reflects to clean energy transitions. And as you can see here, this is really from a fire and gas philosophy, a combination of all the different hazards and the mitigation of that. Yeah, having said this, I've mentioned this already, fire and gas mapping, what is that? If you do not know, and if you have maybe a new application or a quite complex environment, you can simulate that. And there are tools out which are industrial, completely accepted. It gives you, and system compliance here, and system compliance means do I choose the right amount of detectors, the right detectors responding to the hazards as well? And this can be simulated. So that means the input is what the big question is, what detectors will respond to the hazard. So it means I need sensors who are capable of detecting hydrogen. And where should these detectors be positioned? As I said, hydrogen has very special requirements and behaviors in terms of dilution, in terms of also, let's say, leak. When you have a leak, where and how you can expect gas clouds and so on. Maybe you in outside environments, you have maybe wind direction. So it means you definitely have to know where I need to detect my sensors. And at the end, you can model it. That means how many detectors are needed. We talk about costs, for example. And how can I be sure that the area of concern is really protected to an acceptable level? So how this is done, you really having an input document. You see here, for example, a tank area. You simulate that. You put in detectors based on the knowledge that we may have, that you may have as well. And then you simulate that. And then you get, let's say, a coverage where you say, okay, all, let's say, concerned areas, especially from this simulation, are safe. The same can be done also for flame detection. Same thing, same input, and you definitely can see where and how my protection environment is built. Yeah, when we look into something concrete, electrolyzer facility, it's mainly including a storage facility as well, what we see here, or a compressor facility, which is mainly part of it. But looking, let's say, for an example of a larger hydrogen installation. It could be indoors, it could be outdoors. It doesn't really make a big difference now in my overview here. So where and how to install systems. So One of the most prominent sensors and sensor technologies are ultrasonic leak detectors. I have no time today to go into details, but ultrasonic detectors listen to a leak. That means the gas don't have to come to the sensor, which is a big advantage um, because we talked about high dilutable. So hydrogen is a very light gas, but in hydrogen, let's say pressure leak produces a certain sound, a whistle, and this whistle can be detected by a microphone. So this technology is available, which is accepted, and it's one of the most most prominent early leak detection technologies. On top of it, for example, here we see an electrochemical sensors, especially in areas where we, out of the risk assessment, expect maybe a high probability of a leak. This is, let's say, the second layer of safety, which you would put in here. And the third layer is then flame detection. Here also hydrogen is a little bit special. Hydrogen flames, you may know it, you don't maybe know it, are not visible in daylight. You would hardly feel it if you would have a hydrogen flame maybe a meter away from you. You would not even feel it on your skin. It hardly emits IR. So it means you need a special camera, a flame detector here, which very concretely is looking into in hydrogen emission a band, so that with an also very low false positive rate, lowest false positive rate in the market. So we are definitely a technology market leader here. Looking into that so that you have proper flame cameras here around as well. So on this altogether gives you then, let's say, the detection safety infrastructure. All these systems are combined for sure in a system, which gives you then alarm, triggered alarms as well, emergency escape. And all these things will play a role. So that means at the end, we have to trust the technology compared maybe to other gases, methanol, ammonia, for example. Our nose is quite good. But with hydrogen, it's totally different. It's odorless, it's invisible. So that means we have to trust technology. I've mentioned here flame cameras, so we definitely need to look into that. We need point detectors that could be catalytic bead sensors, what I've mentioned here. And last but not least, we can listen to the sound. And we have here ultrasonic gas leak detectors. So this combination of sensors, it could be part of a flame and gas mapping, could be part of a consulting at the end, could be an outcome of your risk assessment. And this is definitely what needs to be known. Having said this, that was my overview.